Good morning, friends. Could somebody confirm whether I'm audible?
Yes, sir, you're audible.
Cool. Okay, fine, good. So let's start. Uh, Good news for you. Homework 3 deadline has been extended. I hope you saw this announcement already, but in case you didn't, then it is October 30, which is day after tomorrow, 11 o'clock at night. And then tomorrow, because day after tomorrow we have a quiz, tomorrow I'll conduct an extra tutorial plus office hour session from 6:30 in the evening to 7:30. Obviously, we'll also have a tutorial session today evening. All right, so let us quickly recap what we did in the last class, right? So we saw two important definitions, one of a permutation group and other of something more general, which is a group, right? So what is a permutation group? So I hope you remember that by SA, if A is a subset, um, yeah, if A is a set, then by SA, script as A, we denote the set of permutations of A, or in other words, set of bijections from A to A. Right, and then we call a subset of this set of bijections a permutation group if it satisfies three conditions. What three conditions? The composition of two bijections in the set must also be in the bijection. It must also be in the set. The identity bijection should be in the set necessarily. And finally, if some bijection is in the set, then its inverse bijection must also be in the set. Right. And then more generally, we defined the notion of a group, right? But before that, we defined what is a binary operation, right? A binary operation on a set A is just a function from A cross A to A, right? So there is just a function from A cross A to A. So it takes two inputs from A and gives an output which is another member of A. Okay, and then if this star is a binary operation, we call A star a group if the binary operation satisfies the following properties. Firstly, star should be associative, and what that means is for all ABC in A, we want A star B star C is equal to A star B star C. Right, so star should have an identity element, which means as let's say ID, which means it should satisfy that for all A in A, right? So A star ID is equal to ID star A is equal to E. And then finally, for all A in for all every element of the set A, there should exist an element B such that A star B equals B star A is equal to identity. And this element is called okay. Let me not call it the inverse for now. Let me call it an inverse of A. And the reason will be clear, right? So we should not really call it the inverse before we prove that there is a unique inverse, right? So let's get that out of our way. By the way, so suppose A star is a group and little a is some element of the set capital A. Can there be more than one inverses of an element? Any intuition? Right. So is the inverse necessarily unique?
Yes, sir. I think it would be unique.
Who is this? Divyanshu. Okay, one sec, Divyanshu. Let me just write the question. Is the inverse of an element unique, or could it have more than one inverses? Why, Divyanshu?
Sir, we can show that we have suppose two inverses, ID1 and ID2. Sorry,
No, not
sorry,
identities.
sorry, sorry. Yeah. Suppose we have an element A and we have got two inverses B and C. So
Okay.
we can take a composition and then I think so we'll be able to show. It will take me a minute. I'll just tell you.
Yeah, okay. Meanwhile, others can think. So how do you prove that? How do you prove that B must be equal to C? So in the meantime, let me just write this down as a claim. Right. So claim let A star be a group and A be an element of the set capital A, then there exists a unique, okay, let A star be a group with identity ID. Let me just add that. With identity ID, and let A be a member of the set capital A. Then there exists a unique B in the set capital A such that what B is the inverse of A, which means A star B is equal to B star A is equal to ID. Okay, so there are three hands. Divyanshu, do you have a proof already?
Yes, sir. So like we can write A star B as ID, and suppose C is the another identity. So like we can take like multiply with C on the left side. Like
C is the other inverse, you mean, not
yeah,
identity.
sorry. C is the other
Okay,
inverse.
then
We
what?
can multiply with C on both the sides, on the left side.
Okay, so then you say that C star A star B is equal to C star ID. Then what?
So then we can say that then we can use associativities and do that C star
Okay,
A
good.
star B equal to C equal to C.
Is equal to C. Okay, so this on the right hand side you use the definition of identity element. On the left hand side you used associativity, and then what?
And then we can write C star A as ID and
Good.
ID into B as B. So B equal to C.
Is equal to C. So therefore B is equal to C. Good. Right. Yeah. So maybe a slightly cleaner way of putting it would be Rajat. Your hand is up. Rajat.
I only wanted to tell the proof.
Okay, I see. Right. So basically, what you are trying to consider is the following element of the group, which is C star A star B. Right. Due to associativity, I can group this. I can put parentheses in whatever way I like. I can say this is equal to C star A star B, and this is also equal to C star A star B. Right, so let me just as well get rid of this. I don't really need this. So these two are equal by associativity. So this is by associativity, right? And now because you know C is okay, I should have stated first, right? I should have said let suppose B and C are both inverses of A. Then we have the following. Right. So this is by associativity, and now because C is the inverse of A, right? So this is just ID star B, definition of inverse. And similarly over here, by definition of inverse, what do you get? You just get C star ID, right? And now by definition of identity, this is just B. And this by definition of identity is just C. Right, so therefore B is equal to C. Right, so every element must have a unique inverse. The fact that the element has an inverse is guaranteed just by the definition of the group. Right, so here therefore we now can say that okay, we can actually replace this and by the inverse of A. Okay, so now let us see a few or rather a lot of examples of groups. So just to get our intuition going, right? So as an abstract definition, it might be clear, but we need concrete examples, right? If there are not too many concrete examples, what is the point in studying some kind of an abstract object? Right, so let us see some examples. Right, so I claim that all of us have seen examples of groups right from the time we started going to school. Okay, probably from day one. So does somebody recall some examples already? Oh well, maybe not the first day of school, maybe in your sixth standard, let's say sixth standard. Maybe not the first day of school. That's too much to expect. Abhinav?
The integer comma like addition or multiplication.
What comma addition multiplication?
Integers.
Integers and addition, and you are saying integers and multiplication.
Yeah.
So Abhinav claims that this is a group and this is also a group. Any objections against this? Yeah, Divyanshu?
So like, I think we would have to claim that for addition, the identity would have to be 0.
Correct.
So in that case, I think it would be a group, but in multiplication, I guess the identity would have to be 1, and I don't think so for all elements we would be able to find an inverse, because like for some of them it would be fractional.
Exactly. So does everybody see the issue why Z plus Z star is not a group? Okay, let's have a show of hands. Raise your hand if you agree that Z star is not a group. Let's see. Okay, quite a lot of people. Okay, then I'm happy. Okay, good. Okay, you could lower your hands now. So Z plus is a group. Good. What other classes of numbers are form a group under addition? Can I add something over here? Something comma plus. Can I add some more sets of numbers over here as examples?
Rationals.
Rationals I could add. Reals I could add. Complex numbers I could add. Right? Cool. What else? I could also say R to the n, right? So n dimensional vectors under the vector addition.
Matrices.
Aradhya, yes, good. Matrices, but all matrices? Is it okay to put all matrices under addition? Aradhya?
They should be of same order, I guess.
Same shape.
Yeah.
Good. Okay. All right. So set of m cross n, let's say real matrices. It could be your matrix could be over any, right? The entries of the matrix themselves could be over any group. That is fine. Still, I can define addition of matrices, right? So set of m cross n, let's say real matrices. Matrices, comma matrix addition groups. So all these are groups. What else? Can you think of a set of numbers which forms a group under multiplication? Right. So we saw that the set of integers under multiplication is not a group. Can you think of a set of numbers which forms a group under multiplication?
Rationals excluding 0.
Rationals excluding 0. Good point. Yes. Right. So yeah, so it could be rationals excluding 0, reals excluding 0, complex numbers excluding 0. All of them under multiplication form a group. Good. So Q minus 0 under multiplication, R minus 0 under multiplication, complex numbers minus 0 under multiplication. What else? Anything from matrices? It doesn't make sense to multiply two vectors and get a vector, right? I mean, there is something called a vector product in 3 dimensions, but For general n dimensions, at least I am not aware of any natural way of multiplying two vectors and getting a vector. But yeah, matrices. Now, definitely we cannot talk about m cross n matrices, right? Because it's just impossible to multiply two m cross n matrices if m is not equal to n. So can I say that the set of n cross n, let's say real matrices and multiplication, is that a group? Set of n cross n matrices for some fixed n. Is this a group? Abhinav?
Sir, we need to exclude the ones which are determinant 0.
Which have determinant 0, and that's because they don't have a multiplicative inverse.
Yes.
Right. So I hope all of you also noted the identities in every case, right? So the identity in all of these cases, right? So the identity over here is 0, 0, 0, 0. It is the 0 vector, and then it is the 0 m cross n matrix over here. Yeah, and then the identity over here is 1, 1, 1. And now, if we try to define some kind of a group over matrices under the multiplication operation, the identity obviously has to be the identity matrix n cross n, and then so what I should write over here is instead of set of n cross n real matrices, I should really write set of n cross n invertible real matrices, or equivalently matrices which have non-zero determinant. Right. Yeah, Abhinav Ramanuj, I'll come to you. Let me just finish off this comment. And this group, by the way, is denoted by GLNR. So what does this stand for? GL stands for general linear group. N stands for the dimension you're talking about. And R stands for the R stands from the set from which you are taking the elements of your matrix. Ramanuj?
So we can also say that positive rationals or positive reals minus 0 is like a group under multiplication.
Absolutely, absolutely. Yeah, positive, yes. Yeah, that's true. That's true. So, right, when you say positive, 0 is automatically excluded, right? Yeah, so similarly, I can say Q plus, comma multiplication, R plus, comma multiplication, and so on. Aradhya?
Non-zero power series.
Non-zero power series. What do you exactly mean by a power series now?
Like a generating function.
Okay, good point. Good point. Generating function under multiplication, right?
Yeah, non-zero.
Non-zero generating functions under multiplication, yes, and similarly or rather all generating functions under addition, that will also form.
Yeah.
Good. Fine. So by the way, we missed out one important example, right? So every permutation group is also group, right? So I hope this is trivial to check. Permutation. Rather, if let us put it this way, if some G subset of SA is a permutation group, then the set G under the composition operation is a group. Right. What else? Can we say actually that some strict subset of the set of integers is also a group under addition? Aradhya, yes? Aradhya, your hand is up. Okay, fine. So my question is, can we actually say that some strict subset of the set of integers under addition is a group? Divyanshu?
So like if we choose some number, say m, and all the multiples of m.
All the multiples of m, that is also a group. Nice. Okay. Right. So multiples of a fixed m in the set of integers and under the addition operation, this is also a group. And this is what we'll denote by MZ. Right, so this group is something we'll denote by MZ. What else? Divyanshu, you're saying something probably. Right. So what about the set? Suppose M is a natural number. Suppose M is some natural number. What about the set 0 through M minus 1 under? Right. So what is this? This is addition mod M. Right. This is also a group. Right. So where the additive inverse of some number j is M minus j, provided j is not 0. If it is 0, then the inverse is just 0. Right. Good. So what else? There is one other example I wanted to specify. Right. So correspondingly, suppose M is some integer. Okay. Suppose M is some natural number. Can I say that this set 0 to M minus 1, right, the possible remainders modulo M, forms a group under multiplication mod M? Is this a group?
I think we
Yeah,
have
Aradhya.
to 0.
Sorry.
I think we'll have to exclude 0.
Let's say you exclude 0. Chalo. Yeah, 0 is not going to have a multiplicative inverse, so let me exclude 0. Now what? Now is it a group? Abhinav?
No, sir, because again, we might not have an inverse.
Can you give a concrete example of some M and some number which does not have an
So,
inverse?
like when the inverse. Oh wait, I'll think.
Saumil?
Sir, if the number has a common divisor greater than 1 with M, then we cannot have an inverse because, like, say,
Correct.
if M is 6 and the number is 2, then you can't multiply it with 1.
Yeah, good. So M is equal to 6, and then you are saying that 2 does not have an inverse with respect to multiplication modulo 6, right? Because anything, I mean, you multiply 2 with anything and go mod 6, you are going to get an even integer. You are never going to get 1, right? So is there a way to, okay, wait, so there are some hands up. Abhinav? Okay, he put down his hand. Saumil?
My hand was already up, but we can take M to be prime. Then
Good. So you are claiming that if M is a prime, then this will form a group 1 through M minus 1 under multiplication mod M. Yeah, we'll see that. Ramanuj?
Yes, I think this is the Chinese remainder theorem.
What is the Chinese remainder theorem?
Or something like that. Like basically, if you have M to be prime, then every integer from 1 to M will have a multiplicative inverse between 1 to M minus 1.
That's not called the Chinese remainder theorem, I believe. Chinese remainder theorem is something different.
I think I forgot, but like there was something like this.
Yeah. Even I don't remember if that theorem is called something, but that is indeed a true statement. In fact, more generally, what we can say is, so this needs a proof, but let me state it right now. Right, what we can say is, okay, instead of this set 1 through M minus 1, let M be any integer, not necessarily prime, right? So set, right, so integers, or rather numbers in the set 1 through M minus 1 that are co-prime to M. Co-prime with him. I don't know what is the right way to say it. Co-prime to or co-prime with. What is the right way? Any idea?
I think it's 2.
You think it's 2? Okay, fine. Let's use 2. Coprime 2L. Right. So this is a group and this needs some proof. So what I will do is maybe I'll add, okay, so prove this, right? So this is a group, right? So I'll add this to the tutorial sheet for you to prove, right? And then let me remark that the proof of this doesn't have much to do with the theory of groups. It has more to do with our basic things, well ordering principle and so on, right? Fine. Right. So now I told you in the last class itself that the primary reason why mathematicians study groups is that groups really represent symmetries of an object. Okay. So let us see an example of that. Although I'm not going to go into the formal details of how do you exactly define a symmetry of an object mathematically, I'm just going to give you an intuitive idea, right? What is the connection between groups and symmetries? Okay, so let us take some examples that we had seen in the last class. So let me add some slides over here. Okay, so let's take this butterfly for now. Right. Right. So if you observe this butterfly, then the intuitive question that we are trying to ask is what operations can I perform on this butterfly so that it still looks the same? Okay, this is a completely mathematically, this is a vague question, but I hope you understand the meaning of it. Right, so what operations can I do on this? Well, there is an identity operation, just don't touch it at all. Right, so there is an identity operation and there is an operation of reflecting about this axis. Okay, so let's call that operation a mirror image. Let's simply call it mirror. Right, so this is our set and our group operation is going to be the following. Right, so let's call the star as the group operation. One way of specifying a group operation is to specify it by a table, right? Right, so if I draw this kind of a table, this is the group operation star. If I have a row corresponding to a group element G, I have a column corresponding to group element G prime, then I can put an entry over here, which is G star G prime, right? So in general, this is one way of representing at least finite groups, if not infinite. Right, so what is the group operation over here, right? So you have ID, mirror, ID, mirror, right? So this is the identity element, obviously. So ID operated with ID is just ID, this is just mirror, this is just mirror. And what is, so if you take a mirror image and then take another mirror image, you'll get back the same configuration, right? So mirror composed with mirror is just ID. Okay, so this is a group of size 2 with identity element, the identity operation, which says just don't touch the butterfly. Right, so similarly, let us take this other simple example. The methane molecule and this Peterson graph are more complicated examples with huge groups. I think the group size over here is going to be 12 in case of methane molecule, and in case of this graph, it is some 120 or something. I think we figured it out. We calculated this in class earlier. Yeah, Divyanshu?
Sir, I was a bit confused in the previous example you showed. So, like, what was the set on, like, can you tell me what is the set and what is the operation in the group?
In case of the butterfly?
Yes, sir.
Yeah, so the set is of 2 elements. What you call those 2 elements is really not important. Okay, so for convenience, I'm calling the first element as ID, identity, don't touch the butterfly, and the second element as take the mirror image. About, or rather, reflect it about, or yeah, maybe it's better to call it reflect instead of mirror, right? Let me just call it reflect. Right, so the reflection operation is with respect to this vertical axis. Reflect.
And so then the star is a composition function, kind of.
Yeah, it's kind of composition function. Yes.
Okay. Okay.
Right. So whenever we are talking about symmetry, the group operation is really saying apply the first function or apply one operation and then apply the other operation. So that's like function composition. Right. So reflect. This is reflect. Yeah, and the inverse of ID is ID. Inverse of reflect is reflect. Right. So now in this case, in case of this flower, if you imagine this kind of symmetry, I mean, if you imagine that all the petals are completely identical, what can I do with this flower so that it appears appears just as it is right now, right? I can obviously always apply the identity operation, right? So now, for lack of better notation, right? I'll introduce the sigma. So what does the sigma tell you? Sigma says you rotate by what is 360 divided by 5, 72 degree. Okay. So if you apply 72 degree rotation, let's say anti-clockwise, then you get back the same configuration. What else can you do? So I can also apply sigma squared, right? So rotate by 144 degree. Sigma followed by sigma. Right? Sigma cubed, sigma to the 4, and now sigma to the power 5 is just the identity element. Right? So if you rotate this flower 5 times through 72 degree, you're rotating it through 360 degree. So you're getting back whatever you started out with. Right? So the set of elements is just this, and then this group operation can be written as follows. Right? So ID sigma squared, sigma cubed, sigma to the 4, ID sigma squared, sigma cubed, sigma to the 4, ID sigma. Then sigma applied to ID is just sigma, the sigma squared, sigma cubed, sigma to the 4, and this ID, and so on. So I hope you can complete this table now. Yeah, Ramanuj.
So don't you also have reflect here as well? And like, will the reflect be
good
different?
Point. Good point. Good point. So we don't have a reflect over here. If you watch if you watch the flower carefully, we don't have a reflect over here. Look how the petals are overlapping. Right? So observe carefully how the petals are overlapping. If the petals were not overlapping at all, then you would also have a mirror image operation available. And that would give you another group. Yeah, Aradhya?
So I think the mathematical term here would be that the object is chiral.
Is what?
Like the mirror image is not superimposable with the object.
So what is it called? Chiral spelling?
CHIRAL.
Okay, I was not aware of this term. Okay, good to know. Good to know. All right. Thanks, Aradhya. Okay, good. Fine. Right. Okay, so I hope this much discussion is enough to show the connection between groups and symmetry. Aradhya, your hand is still up. Did you want to ask something? Say something? Okay, fine. Right. So the formal, I mean, if you're curious, the formal thing you should look for, if you're curious to know what is the exact connection between symmetries and groups or the mathematical connection, what you should look for is something called a group action. Right. So I'm not going to go into the details of this thing. Abhinav?
Sir, you said that if the petals are not overlapping, we'll have another group which will have reflect, right?
Reflect also, yes.
Why can't we have one single group which includes rotate as well as reflect? Like why
that's what
separate?
I said. No, that's what I said. The set of, right. So the set of symmetries will include the reflect operation and it will be a larger group. I'm not saying you have two groups. I'm just saying you have a larger group than this.
Okay.
Okay. Is that okay, Abhinav?
Yes, sir. Fine.
Okay, good. And probably we'll see that in either in today's lecture or next lecture. What happens if the petals are not overlapping? What kind of group do you get?
So we can also have
Yeah.
reflection of the object about any point on the stem of the flower.
What now? It is a well. So it has 5 petals, right?
No, reflection of the object across any point on the stem.
Across any point on the stem, right? So that's
Yeah.
what I'm saying. So you have 5 petals in this case.
Yeah.
Now a petal in that case will go to a location which is between 2 petals in right now, right? So
Yeah.
if I simply represent this, sorry, if I simply represent the flower like this is the best way I can draw a flower, unfortunately. So if you're okay, you're trying to say let us reflect about this point, right? So now this point will go somewhere over here, and now the flower will start looking something different.
Yeah, but sir, the orientation would also be reversed. Like the sense of the petals would also reverse, and the orientation, like the side on which the flower is facing, would also get reversed. So both of them would
Right.
cancel
So
each other out.
anyway, the point is that it will not look the same, right? So if you close my eyes and you do this operation and then I open my eyes, I will be able to tell you that look, you did this, right? But on the contrary, if you do any of these rotations, I will not be able to tell you which one you did. Right, Aradhya?
Oh, right, we're not allowed to freely rotate the object.
No, of course not. Of course not. Then it would not be a symmetry at all, right? I mean, if you're allowed to freely rotate an object, you could take a perfectly, you could pick up a stone and then call it say it has so much of symmetry, right? That is nonsense.
Yeah.
Right? That is not what we're looking for.
Yeah.
Okay, Aradhya? All right, sounds good. Okay, right. So yeah, let us come back to this tons of examples that we had. Right. So now think about this. Out of these, whatever, I don't know, maybe around 20 examples, maybe slightly less. Can you identify how many? Right. So can you identify 2 examples which are kind of different from the rest? And can you tell me the reason why you think they are different? Okay, so people don't seem to be having an idea. So let me point out which 2 examples, and now maybe you'll be able to guess what is the reason I'm calling them to be different from the rest, right? So one is this one, set of invertible matrices under multiplication, and the permutation groups. How are these 2 different from the rest? Rishabh?
Non-commutative.
They are not commutative. Absolutely. Right? So, except for these 2 examples, look at any of the group operations, right? Except for these 2 examples, all the group operations satisfy the following additional property. What is that additional property for all A, B in the group? A star B is equal to B star A. Right? Whether it is integer addition, whatever, non-zero rational number multiplication, or it is addition modulo M, multiplication modulo M. All of them satisfy this property, and which is called commutativity. So commutativity is not a prerequisite for something to be a group, right? So the group operation is allowed to be not commutative, right? Like in the case of matrices, and the composition operation in case of permutation groups, right? But if it turns out that your group operation is commutative, right? So then these groups are in some sense special, and then they deserve to be called with a different name. Okay, so let us do that. Right, so let us define definition. A binary operation star on a set A is said to be commutative if for all elements xy in A we have x star y is equal to y star x, right? So definition, if G is equal to, let's say, A comma star is a group and the group operation star is commutative, right? So then G is called naturally a commutative group and it also has a different name. It is also called or an abelian group. So this word abelian comes from the name of a mathematician. I forgot the first name. The last name is Abel, right? So yeah, so such a group is called an abelian group. So basically, all the examples that we saw over here, except these two, were abelian groups. So similarly, both of these were abelian groups. Okay, right. But obviously, not all groups are abelian groups. Okay, any questions up to this point? Let me pause for half a minute, let's say. Okay, cool. Fine. So apparently there are no questions. So let us go ahead. Right. Okay. So now let us revisit one of the examples that we saw earlier. Okay. Right. So we have seen that the set of integers with respect to addition is a group, and the set mz, right, which is the set of multiples of the integer m under addition, is also a group. Okay, right, and obviously this mz, the set of multiples of the integer m, this is a subset of z, right? Moreover, this addition operation is same in both cases, right? So the meaning of addition operation is the same. I mean, you add two. Okay, let's say you have two multiples of m. Whether you add them with respect to this group or you treat them as members of this group and add them, it doesn't make a difference. Okay, so such a group, right? So if you have this kind of pair of groups, then you will say that mz comma plus is a subgroup of z plus, right? I'll write down the definition formally, right? So the set of elements must be a subset and the group operation must be the same. That is the important. That is equally important thing. Okay. Except, I mean, yeah, basically, except note that this group operation is just the restriction of this group operation to the set MZ. That's all. Yeah, Divyanshu.
So, sir, like this definition is analogous to like the one we do in vector spaces. Like we have a space and we have a subspace.
Vector spaces, you have a space and then subspace. Yes, good point, Divyanshu. So actually, can you see a connection between vector spaces and groups over here already, since you mentioned this? Right. So vector space is a group under addition, obviously. And the subspace of a vector space is a subgroup of that group.
Yeah, something like that.
Right. So you take two elements of a subspace, you add them, you get another element of the subspace. So the subspace itself is a group under the same group operation. Right. So therefore, a subspace is a subgroup of the whatever underlying whatever bigger vector space you're talking about. Yeah, good point. Okay, so let us formally define this. Okay, but before we formally define, let me introduce some notation. Let me introduce some notation. This will be convenient for us to work with to avoid unnecessary symbols. So, right, if let G equal to, let's say, A star be a group, right? So then we write right. So X belongs to G is same as saying X belongs to A. Right? When we say an element belongs to a group, we actually mean that it belongs to the set part of the group. Similarly, we could say right. So H is a subset of G for right. So if H equal to some B star, right? Okay. Possibly some different operation. I don't care. When I say H is a subset of G, I really mean B is a subset of A. Right. So whenever I use any set operation on a group, I really mean I'm talking about the set part of the group. I'm ignoring the group operation. Right. So now let's define. Let G be a group and star be its group operation. A subset H, which is a subset of G, is called a subgroup of G if H under the operation star is a group. Importantly, the same operation star. Right. So note, right. So let's say Q minus 0 under the multiplication operation is not a subgroup of Q under the addition operation, for example. Why? Because the group operation is different. Identities are different. I hope it is clear that if this happens, if H is a subgroup of G, then the identity element of H is same as the identity element of G. In particular, other way of saying it is that the identity element of G must belong to H for H to be a subgroup. Right. So let me also say that IE. I mean, okay, let me not write it. I mean, I hope you understand, right? So H itself is closed under under the star operation, identity of G belongs to H, and then if some function if some member f of G belongs to H, then f inverse must also belong to H. Right? That is what is implied by saying that H is a group. Okay. Any questions? Okay. All right. Now let us once again revisit the relationship between mz plus, which is a subgroup of z plus. Let us inspect and see whether we can find something interesting there. Okay, so let's say m is equal to 3. Let me draw this number line. Right, so so how does the group mz look like? Right, so mz, so everything in pink is a part of mz. So 0 is here. Right, so 1, 2, 3, 6, minus 3, minus 6, and so on. Right, it extends kind of to infinity in both directions. Right, so now as soon as we define this, as soon as we look at this subgroup, right, what we should immediately notice is the set, right? So this is the set of, right? So everything in pink is the set of elements which are 0 mod 3. Let us also look at the elements which are 1 mod 3, right? So this is 1, this is 4, 7, minus 2, minus 5, and so on. Right? So what is the orange set? Right? So the orange set is the set of numbers which are 1 mod 3, or in other words, it is the set of all numbers of the form 1 plus g, such that g is in 3z in this case. Similarly, if I draw another set over here, the set of numbers which are 2 mod 3, right? So this 2, 5, minus 1, minus 4, minus 7, right? So this cyan set is the set of all numbers of the form 2 plus g, such that g is in 3z. Right, so after all, what are these sets? What is the orange set and what is the cyan set? It is just the original subgroup, except that it is kind of shifted. Okay, shifted by some fixed element of the group. Okay, right. So this is what we will call a coset of a group. Yeah, Abhinav.
So like these orange set and cyan set even in groups, because we don't have identity element, right?
Those are not groups. Of course, they are not groups. All I'm saying is there some kind of a shifted version of a group, and due to the shifting, it has lost the identity element.
Okay, fine. Okay.
So just like in your example of vector spaces, right? So let us take another example. Okay, so this 3-dimensional vector space is a group, right? So suppose this is x, y, z axis. This 3-dimensional vector space is a group, and then the xy plane is a subgroup of this group. Now, what if I take a fixed vector? Let's take some fixed vector. Let's take this fixed vector, which is not in the plane xy plane, and add this vector to every vector in the xy plane. What will we get? Right. So by the way, this is this plane is extending on both directions. It's not like a quadrant or something. Yeah, so if we add this fixed vector to every vector in this plane, what will we get? We'll just get a shifted version of the plane. You will not get a subspace, but you will get what is called a affine subspace. Right? So you'll get this shifted plane. Analogously. Okay, so right. Yeah, so let me just define this notion of a coset, and then we'll see what interesting properties we get out of that coset. This notion of a coset. Okay. Right. So another bit of notation. Sachit.
So why the orange set is not a group?
The orange set is not a group because the identity element is not in the orange set.
Like can't.
Okay, I should ask you the question: orange set under what operation? Orange set under what operation? If you're trying to say orange set under the addition operation, usual addition operation, then it is not a group because the additive identity is not in the orange set. Okay.
Can't we say 2 is additive identity?
2 is identity, but 2 is not even in the orange set, no?
Oh, okay, yeah, sorry.
Why would you say 2 is an identity in any case? Let's say in case of the science set.
Like I thought about shifting it, like in that case, sorry, got it.
So you're defining a new operation. What you're trying to say is map it back to the original subgroup, operate on the subgroup, and come back to the coset. Yeah, there is obviously, given a set, there is always a way of defining a group on that set.
Yeah.
Appropriate group of operation on that set which will form a group, but then that's not what we are talking about. We are talking about subgroups of a fixed group MZ. Right? So the orange set and the cyan set are not subgroups of MZ. Why? Because firstly, I mean, trivially, they don't include the identity element itself, and moreover, they don't include inverses also in this case. Right. So let us set up a notation. So if G is a group, H is a subgroup of G, and let's say little g is an element of the group G, then GH denotes the set GH such that this element H is in H. Intuitive, right? So take every element of H. Sorry, I should have mentioned the group operation, right? With group operation, let's say star, and then here I meant to write G star H. G star H is this, and similarly, G star H is the set G star little h such that this little h is in H. Just a short form that I'm introducing. And similarly, I'll say H star G denotes the set H star G such that H is in H. Okay. So definition. Right. So let G be a group and with group operation star and let H be a subgroup of G then the set H be a subgroup of G and G is in capital G. Okay, so then the set G star H is called a left coset of H, and similarly I'll call the set H star G as a right coset. Right, so why am I being so strict about calling it a left coset and a right coset? The reason being, this star in general need not be a commutative operation, right? So we'll see an example of a group which is not commutative, and in which case the left coset is not a right coset, and vice versa. Right, so there are cases in which this notion of being a left coset and right coset, these are two different things. Okay, so right, so therefore this orange set is really a coset of the group MZ, cyan set is another coset, and then this subgroup MZ itself is a coset by definition. Divyanshu?
So can you tell the definition of coset again? I didn't get it.
So look at what we did over here, right? We had a subgroup MZ. We took one element of the original group, let's say in this case the element 1, and we added it to every element of the subgroup. We perform the group operation of that single fixed element 1 with every element of the subgroup. What we get out of that, right, it's some kind of a shifted copy of the subgroup, and that is what we call a coset. So if we operate the fixed element from the left, we call the resulting set a left coset. If we operate the fixed element from right, we call the resulting set a right coset. That's it.
So like,
is it okay?
Yes, sir. So basically we are calling the orange set and the cyan set a coset, right?
Yes.
Okay. And sir, if star is commutative, and if we choose the same small g, then both the left set coset and right coset would be same, right?
Are going to be the same. Yes, of course. Good observation. Yes. Right. So if G is a commutative group, or in other words, an abelian group, then every left coset of G is also a right coset, and vice versa. Right. So let me just state that observation over here already. If G is commutative, is a commutative group, then every left coset of G is also a right coset, and vice versa. Right. Okay. Fine. Right. So let us see an example in which the left cosets, this collection of left cosets is not the collection of right cosets, and vice versa. Yeah. So yeah, this is not what we want. Right. So let us take, okay, example. Suppose our group, the parent group G, is just the set SA, right? A is some finite set. Okay, and I'm looking at all the permutations over the set A, and my group is just the symmetric group over here. Now suppose Z is some element of A, right? So I have Z somewhere over here, right? So let me draw the kind of Venn diagram. Right, so this is my set A is a finite set, let's say, and Z is some fixed element of A. Right, so now let fix Z be the set of all permutations F in SA, such that F of A is equal to, F of Z is equal to Z. Right, so this is the set of all permutations of the set A, which just leaves Z unchanged, which maps Z to Z itself. And then the other elements could be mapped in an arbitrary way. Right? So observe that this is a subgroup of G, right? So check that. Fix Z is a subgroup of G. Right, so actually, let me make a slight change. Let me call this G to denote, to indicate that it's a member of this group, right? So fix Z is a subgroup of G. Why? Because identity permutation leaves Z, maps Z to Z. If two permutations map Z to Z, then their composition also maps Z to Z. And similarly, if a permutation maps Z to Z, then its inverse also maps Z to Z, obviously. Right, so now what is, how do the left cosets of fix Z look like? Right, so how do the left cosets of Z look like? How do you construct a left coset? You take an arbitrary permutation in SA, right? So you take an arbitrary permutation F in SA, and then you consider the set F compose fix Z. Okay, right? So which is the same as the set, sorry, F compose G such that G of Z is equal to Z and G belongs to SA. What is the property of this set now? What is the nice property of this set? Right? I'm looking at the set of all bijections of the form F compose G, where F is some fixed bijection and G is an arbitrary bijection which maps Z to itself. Okay, so what does F compose G map Z to? Right, so this F compose G, what does this map Z to? Right, so this is just F of G of Z, but G of Z is Z, so this is just F of Z. Right, so every element of this coset takes this element Z to some fixed place. Right, so this is F of G, F of Z. Every element, so this is just the set of all elements H of SA, such that let's call this element B maybe, or let's call this element Y. All H such that H of Z is equal to Y. Right, so as you vary Y over elements of this set A, you will get different cosets. Right, so every left coset of the set fix Z is the set of bijections over A which map Z to some fixed element, and the coset which, right, so the coset corresponding to the element Z itself is just fix Z. Okay, raise your hand if this is not clear. Divyanshu, do you want to ask a specific question or do you want me to explain once again?
So like, would you just wait over here for 1 or 2 minutes? I would just read it again.
Okay, fine. Sachit?
So what do you mean again by specific element? Like I got FGZ is FZ. Like,
So what I'm saying is, right, so what I'm saying is the following, right? So let Y, okay, forget this. Let Y be any element of the set Z, a set A. Right, so how did we define fix Z? Fix Z was the set of bijections which map Z to itself. Instead of that, I'm saying look at all bijections which map Z to Y.
Okay, okay, got it.
Right? What is the relation of this set with fixed Z? Right? So every element of this set is going to be of the form F composed with some element of fixed Z, where F is any fixed bijection which maps Z to 1.
Yes, sir.
Okay. And similarly, what do right cosets of fixed Z look like correspondingly? How do the right cosets of Fz of fixed Z look like? Right, so let us do the same thing once again. Suppose F is in SA, then fixed Z compose F is the set of all G compose F such that G of Z is equal to Z and G is in SA. Right, so what is this? So this is the set of all H in SA such that what should I write over here?
So h of y is equal to z, where y is some element.
Yeah, I'll use a different name now. So this is the set of all functions such that h of x is equal to z, where x is equal to z, where x is some fixed element. Right. So where what is x in this case? X is just f inverse of z. Right. So moral of the story is if you look at fixed z, which is a subgroup of the symmetric group, then the left coset, every left coset corresponds to a set of functions which take z to some fixed element, and every right coset of this subgroup corresponds to the set of functions which take some fixed element to z. Right, so this kind of an edge, right? So this self loop z, this self loop is something which defines, so this self loop defines the set fixed z. This kind of an edge really defines the left coset of fixed z, f dot fixed z. And similarly, if I draw another element, this element could possibly be just y, but I'm just drawing it as a different element. So this kind of edge is going to really represent, right? So every right. So you take a permutation, you look at its cycle representation. If the cycle representation contains this edge x2z, right? So the set of all permutations whose cycle representation contains this edge is really a right coset of the z, fixed z. So it is fixed z composed with some fixed z composed with some h, let's say. No, sorry, f. Right, so I hope you can see that, right? So a left coset is not really a right coset in this case, right? So yeah, so except for, so check, except for the coset fixed z itself, no left coset of fixed z is a right coset of the fixed z. Right, so I'll also include another exercise in the tutorial which will give you more intuition about this. So this is something you'll have to just work on your own to get an intuition of, right? I'll give you another example of a non-abelian group in which case you can just verify, right, so that the left coset of that group of a subgroup is not equal to right coset and so on. Okay, any question? Yeah, Shamoon?
Sir, when we define the left and right cosets, the function, the element f the element f can be any element in G in our group.
Any element in the group, yes.
Yes, sir. Sir, if f is in G, I mean if f is in fixed Z, then in that case the left coset and right cosets would be same, I think.
Would be just fixed Z. Yes, you're right. Absolutely. If your f element that you right, so f is allowed to be any element in the set G, but if f itself is in the subgroup, then the left coset as well as the right coset that you'll get out of that element is just the subgroup itself. Nice observation. Yes, you're absolutely right. Okay, awesome. Awesome. So now, right. Okay. Okay, what did we want to prove now? Right. So let us just write down a couple of observations, and then using those observations we'll get a rather important result. Okay. So right. So suppose H is a subgroup of G of group G with operation, let's say star. Okay. Right. So let's just worry about left cosets for now, and analogous statement can be made about right cosets also, but we'll just pick one of them. Let f be some element of the set of the group G. Okay. So then I want to claim that there exists a bijection. There exists a bijection between H, the subgroup H, and its coset F star H. Right. So let me state this as a claim. What am I trying to prove out of this? All I'm trying to prove is that every coset has the same cardinality as the subgroup. Every coset, whether left or right or whatever, of a subgroup has the same cardinality as that of the subgroup. And what is the long-term plan? Firstly, I'm proving that the cardinality is the same. Secondly, I'll prove that the cosets kind of partition the entire group nicely. And as a consequence, I'll prove that if your group itself is finite, then the size of the subgroup divides the size of the group. That is the rather strong statement I'm heading towards proving. Right, so let us make this a claim. Just happened. Okay. Claim. Right, so can somebody just suggest an explicit bijection between H and F star H? Right, so what is F star H? I mean, if I just write down the definition of F star H once again, the bijection should be obvious, I hope. F star H is just the set of all F star, let's say H, such that this little h is in the set capital H. What is the bijection? Right, I want some function going from H to F star H. Bijective method. Right, it's right in front of you. This is the bijection, right? So H H in the subgroup goes to F star H. That is the bijection. Of course, we need to prove that this is a bijection, but as of now, this is just a function. Right. So, right. So it should be clear that this function is a surjection. Why? Because if something is in is in the set F star H, the only reason it can be in F star H is because it is of the form F star little h for some little h in capital H. So that little h is going to get mapped to F star H. Right. So this is clearly a surjection. Right. So I should rather write H going to F star H is clearly a surjection. By definition of F star H. Why is it injective? Right? Is it possible that H, right? So is H gets mapped to F star H, some H prime gets mapped to F star H prime. Is it possible that these two are actually equal? Somil?
No, because we can multiply with F inverse on the left to get the H equals H dash.
Absolutely, absolutely, absolutely. You're right. Okay, so this is injective because if right, so if F star H, right, so injective because if F star H is equal to F star H prime, right? So then what do you have? Left multiply, or rather operate F inverse from the left on both sides. So then what do you get? Let's be careful about it. F inverse star F star H is equal to F inverse star F star H prime, right? And now by associativity, what do you get? F inverse star F star H. F inverse star F star H prime, right? So this is by associativity. And then this is just the identity, this is just the identity. And therefore H is equal to H prime. Right, so one important consequence of the existence of identity is that we can cancel out things the way usually you do in case of integers or whatever, real numbers. Right, so if the inverse does not exist, then you might not be able to cancel out things, right? So this is what the existence of inverse gives us. Right, so now any question? Okay, right. So raise your hand if you think this was a bit too fast, because I'm not seeing a lot of response from the audience. Raise your hand if you think this was too fast. Okay, fine. All right, sounds good. Okay, nobody claims that it is too fast at least. Right, so let me just add a justification over here. So definition of inverse, and this by definition of identity. Right, so what does that mean? So this means that the cardinality of a coset of a subgroup is just equal to is same as the cardinality of a group of the subgroup itself. Right, so we just have 4 minutes, so I'll not start with the other part of the proof, which says that the cosets kind of nicely tile the entire group, right? So the next claim that we'll try to prove is that if this is your group G, and let's say this is your subgroup H, right? So H is a subgroup of G. And let's maybe look at the left cosets. Everything that we say about left cosets is also equally valid for right cosets. So let's say these are the left, right? So the left cosets are going to look something like this, right? So these are the left cosets of G, H. Each of these is a left coset of H. And they are going to nicely partition the entire group. And as a consequence, what will you get? So as a consequence, you'll get that if G is a finite group, obviously H is also a finite subgroup of G. Then the size of all these cosets is the same, and therefore the size of G is divisible by the size of H. Now, if you recall that in the last class, when we tried to find all permutation groups over a set of 3 elements, what did I say? Right? So the symmetric group has size 6. So therefore, you should only look for groups of subgroups of size 1, 2, 3, and 6. That's all. Right? So that is the reason why I said so. Right? That is the reason why I claim that you cannot have a subgroup of size 4 in that case. Okay, we have 2 minutes before we end the lecture. Right. Any questions, comments? Anything to be repeated? We'll finish this off in the next class. Right, so since we have 2 minutes, maybe I'll just state the high level plan of what we are going to do in the remaining 3 lectures of this course. We'll obviously finish this. We'll see the notion of, right, just like you have a graph isomorphism, we also have group isomorphism. Right, so 2 groups essentially have the same structure. It's just that they are kind of renamed versions of each other. Then we'll call them isomorphic. We'll define this formally, right? So that way we'll get done with the elementary group theory. And then we'll see some small applications of group theory to prove some number theoretic results. And as a consequence of those number theoretic results, you have some nice cryptographic protocols and so on. All this is depending on how much time remains. Okay. All right. So time is almost up. So unless there are any more questions, I'm going to stop the recording, end the class, and then we are going to meet in the evening for the tutorial session. Reminder, tomorrow again we'll have another tutorial session plus office hour. So feel free to attend. Ask whatever questions you want to ask. All right, chalo then. That's it for today.